Yeah, thank you very much for this excellent introduction. Just want to say I'm one of multiple founders of SK Time. So there's also Anthony Bagnall and Marcus Learning to mention. I'm really thrilled to be here in Berlin in person. This is actually the first big presentation I'm giving since Corona in front of people. And as we all know, our social skills have suffered. So if you see me behind the desk here, don't worry about it. Now, I will give the first part of this presentation, which is introduction, tutorial, and a tutorial into new probabilistic forecasting capabilities of SK Time, the machine learning toolbox for learning with time series. Daniel will give the second part on hierarchical and global forecasting. There will be opportunity for questions after the probabilistic part, after the hierarchical part. These notebooks, there is 3 in total. You can find them on this GitHub page. It's the SK Time org, SK Time tutorial PyData Berlin. Maybe one note ahead. The newest version of the packet which is required is not yet on Conda. Which is required to run the binder. So at the moment, you should be able to run it using a pip install or developer install. Right, all the links for that have been pasted into the Discord of PyData Berlin in this room. And also in general, right, if you have any technical problems, say you want to install SK Time, you think there is a bug, which there of course always might be. I'd say volunteer-driven project mostly. You can go to the Slack contributor, this SK Time Slack, the contributor channel, or the discussion forum on the SK Time GitHub to ask any questions. So, what is SK Time? If you haven't heard of it yet, it is a scikit-like learn toolbox and really meant to be inspired by scikit-learn interface is an architecture for learning with time series. I'll explain more about that below. It's open source, permissive license, Python, of course, we're PyData. It's openly governed, so we're trying to maintain an approximately equal split between academic, industry, and early career contributors. Currently, we have 18 core developers, out of which I think you can meet 3 here at the conference, and a couple more right now in the Slack and Discord channels. We're NumFocus affiliated since recently and also affiliated with a number of academic centers in the UK. Now, it's openly governed, so contributions are very much appreciated. Right here, this link gets you to the Getting Started and Contributors page. You can join our Slack and Discord very easily. There's regular community collaboration sessions. Every Friday, there's 2 currently, but depending on interest, we may arrange more where you can just join, ask questions on how to use or how to install SK Time, or join developer discussions, how to start contributing, for instance, or just if you want to meet the SK Time developers. We'll have internships this summer. There's a community onboarding event for those who want to start contributing at the end of May, and we'll have a developer sprint in June, which you can join if you want. There's also job opportunities related and mentoring opportunities related to SK Time. So soon there will be a maintainer job. So maintainer/researcher, so it's a combined role, advertised at one of our partner universities, the University of East Anglia. There's a mentoring program that's unpaid, but you pay in a sense with your contributions for the mentoring time. There's various options there, and paid internships. We're currently, this year, 2022, part of Google Summer of Code as an organization. You can still apply. There's 1 week. Deadline is April 19. Again, you can find details on the mentoring page, or if you just go on the SK Time developer documentation, you'll find at the very top application link for Google Summer of Code. All right, so, sorry? Oh, is it okay? Can you see this, or do you need to zoom in? Can zoom in further. Is this better? Should I zoom in further? Who thinks I should zoom in further? Who thinks I should zoom out further? Who thinks it's exactly right? Okay, I'll keep it like this then. So there's a correlation with how far you are from me. I don't understand why that is. But you can find these notebooks also online, and you can open it on your screen. All right. So, scikit-learn-like toolboxes. SK-Time is a scikit-learn-like toolbox, but what does that mean? And maybe 3 points I just quickly want to highlight to understand the philosophy behind SK-Time. So what makes scikit-learn so great, and one of the cornerstones of modern machine learning and AI in practice, it's the unified APIs and workflows. So algorithms of the same type are available under the same API. They can be integrated and exchanged in specific workflows. The individual algorithmic components are easily composable. You can arrange them, for instance, in pipelines, and the pipeline, again, follows the same interface of the components, and it's open. So open to extension, also to third-party extension. It's easy to implement your own estimator, your own algorithm, and have it interface with all the workflows and composition patterns. You don't need to contribute to scikit-learn directly, or there's no license issued attached, because the extension interface, the extension contract, is also public. And these 3 points, as well as specific aspects of the scikit-learn architecture, we're also trying to follow with SK-Time. So if you look at scikit-learn, if you haven't seen scikit-learn yet, I would strongly recommend to look at it. So one of the core workflows is the fit and predict workflow, the deployment workflow, or the evaluation workflow, depending on whether the predictions are made on data where you already have ground truth labels. So this is supervised learning. So first, right, we load our data. X, the rows are features. Y is a vector of labels of equal length as X. What we want to do is we want to train an algorithm to predict Y from X on data from a similar source, jointly ID. Formally, right, in the second step, you specify your model, and this can be arbitrarily complicated, can be a composite pipeline. You can specify model components and build more complicated models out of the model components. sklearn provides a functional syntax to combine individual algorithm components into a composite. Then, whether now you choose the random forest regressor or any other regression algorithm, the remainder is exactly the same. Right? You fit to the training data, you predict on the test data. So up until forward, that's how you would deploy. And if you want to evaluate how good your algorithm performs on historical data, on data you've already seen, you can then run functionality for evaluation on top of it. Right? So that's the basic workflow, emphasizing all algorithm. Right? There's dozens of algorithms that you can choose from in scikit-learn, and all the changes, if you want to use a different algorithm here, is this part. So instead of 99 trees, I could choose 100, and the rest would be the same, or I could write something much more complicated, and it still would be much the same, as long, of course, as long as you deal with supervised regression. If it's a different task you're looking for instance, clustering, then these steps will change, but still they will be similar morally. As I mentioned already, modular model building. So pipeline is one of the core pieces that can compose algorithms into a more complex one. Grid search is another one, which is not shown here. So just as an example, this would then replace step 2, the model building step above. Here we have 2 components, a standard scaler and a k-neighbors regressor, which you compose into an estimator that again has the same familiar fit predict interface as we see here, steps 3, 4, 5. Okay, so now SK-Time, trying to do the same for time series. And why is it not just, okay, now we can just use scikit-learn for everything? The high-level story here, there is a wealth and breadth of data formats, so what time series can mean, what it can imply, and a wealth of algorithmic tasks that you can try to do or try to solve with time series. So supervised learning is, I think, one of the most widely understood learning tasks, but it's not specifically a time series task. In time series, you have this interaction of the different learning tasks and the properties of the data format that you now need to start to deal with. So in consequence, it also means you have many more different types of algorithms and properties of algorithms. So one example is the distinction between univariate and multivariate. Okay, scikit-learn also has that as well. When it comes to prediction. The other feature is ordering, right? So the data are ordered by time index, whereas in supervised classification, supervised regression, you do not have any particular order. So in forecasting, you want to forecast into the future, for instance, of this time series, and the future time points are not, the observations, the values are not coming from the same distribution as the past time points. Past performance is not a guarantee for future performance, for instance. You may have heard that sentence. In time series, you also have multiple observations, and then you have this combination of sequentiality and multiple types of observations in this example. So another maybe more interesting, and that's a significant departure from the data formats in scikit-learn, is panel data, where you have multiple observations over time of multiple systems or multiple independent experimental units. For instance, multiple patients all being observed over time. So you have the dimension time, you observe one object over time, but you also have the different objects. Whereas in classical supervised learning, you have only the object dimension, you do not have the time dimension. So in this setting, you have instances, you have the different variables, and you have time. So already you have three ways, three dimensions across which your observations of variables can vary. And of course, that's only the data. That's not yet what you can do or want to do with the data. When we get to that, there is also a variation that is, in a sense, orthogonal from the temporality, the multiple observation issues in the data format. So for instance, we have forecasting, you have a time series, you want to predict ahead in time. We have time series classification, so your samples are entire time series. You want to attach one label to each time series. So that happens on panel data, because you have multiple instances, and to each instance you want to attach a label. It's different from forecasting or time series annotation tasks. For instance, you may want to segment a time series. Inside the time series, you want to find change points or outliers, or of course you also have the unsupervised tasks like clustering. Within forecasting, there are variations, some of which we will see today, which are common in applications. So you have, if you want to forecast, you can do it for a single time series. For a panel, you can have additional information on the time series in sense of a hierarchy. So different units being observed, and those units add up or are contained hierarchically in other units. We'll see this in the second part. And of course, as in supervised learning also, there is the distinction between, do you want to make do you just want to predict a number, or do you want to predict, say, a range in which this number can lie, or distribution? Now, this wealth of data formats and learning tasks also comes with relations between those learning tasks. So you can use, for instance, an algorithm for task A to solve task B. A very common example in forecasting would be running over time series with a sliding window approach, taking these sliding windows and getting them in X and Y format like you have in supervised regression, then applying a supervised regressor. That act of doing that, as shown in this picture, is an act of reduction, the technical term. So reduce forecasting to supervised regression. You use a supervised regressor to make a forecast. The supervised regressor does not become a forecaster, but you have two pieces of the algorithm, the supervised regressor, the little robot, and the other part of the algorithm, which is an algorithm composer, like a pipeline that contains the supervised regression algorithm, but itself it's a forecaster. And this act of composition, we're also trying to draw out and make very explicit in SK-Time, similar to the composition constructs that are available in scikit-learn. Philosophically, we're trying to build a framework, so there's a lot of individual algorithms floating around and packages that, in a sense, are between individual algorithms and frameworks. So, for instance, Facebook Profit is a very popular algorithm, or PMD ARIMA has a number of statistical algorithms available for forecasting with varying interfaces. And we're really trying to define an API, a unifying interface where we can present different objects, algorithms, or performance metrics under the hood, where you can easily combine them using composition patterns, as we've just seen in the reduction example, and which also helps to tie an open ecosystem together. And currently, SK-Time is a combination of interfaces to other packages and algorithms individually implemented. That's a little bit different from scikit-learn, but long-term also we would like to get to an ecosystem where we have the workflow, the interface elements, and then separate pieces of the ecosystems in which individual algorithms or composition elements are sitting. Right. So you can read up more on frameworks, and if you're now interested extending or presenting algorithms in a unified format, you can also look at the extension templates and the developer guides here. There's also, I want to mention, a research angle to SK-Time. So we're also quite involved in academic research, cutting-edge research. Research groups all over the world make their algorithms available with SK-Time compatible format, sometimes directly in SK-Time, and then using them in benchmarking studies in a hopefully very reproducible way. We have a lot of community building. I mentioned Google Summer of Code. I mentioned the regular Friday sessions. So you are very much welcome to join that journey. All right, that's the introduction. And then I'll proceed to the new probabilistic features. How we're in terms of time? 10. All right, so probabilistic forecasting. Next notebook. So this notebook has more content than I will be able to show in the time, but it's more there for completeness. It's still meant as a tutorial notebook. So what I will show is a quick start, some explanations of what does it even mean to make probabilistic forecasts. Right? Sometimes a lot of different concepts are bunched together under this header. Then how do you do probabilistic forecasting in SK-Time, metrics and evaluation, advanced composition, and at the end is an extender guide. I only skim over that. All right, so probabilistic forecasting with SK-Time. Philosophically, as we've said, we want to stick to scikit-learn-like interfaces, which means we have designed our workflows very much around this. This is the non-probabilistic workflow. Looks very much the same with slight differences to the scikit-learn interface. So for forecasting, right, you only fit to the past time series and possibly exogenous data. So that's the X, but it's not shown here. And the forecasting horizon, which is a representation of the time indices for which you want to make a forecast. So for instance, if you look at the airline data on the previous slide, remember these were just observations monthly up until the year 1960 or so. And now we say, okay, we want to predict from this Y 3 months ahead. That's January, 61, February, and March. And the predict interface here would give us point forecasts, so just one value per month. So you can see all of that in the general PyData Global, the PyData Global tutorial for SKTime, which you can visit here using the link at the top of the first notebook. The probabilistic interface works like that. So for instance, we can use this function predict interval with and giving to it a nominal interval coverage for the forecast, and it will forecast a lower and an upper value of an interval with this nominal coverage, 0.9. So we expect in this case, for instance, 0.05 or 5% probability, nominal probability for the value to fall below, and 5% nominal probability for the value to fall above the upper here. So that's the general gist of it. It works exactly like the non-probabilistic interface. And now let's look at the different methods in SKTime that are available for probabilistic forecasting. There are currently 4 different methods corresponding to different kinds of probabilistic forecasts, which I will also explain in a moment. It's just a quick start. So predictive intervals are available under predict interval. We have forecast quantiles, and these forecast quantiles are at quantile points or quantile values. The forecast intervals are symmetric and at a given coverage. Forecast variance can be obtained using predict_var, and depending whether you have cov equals false or not, you get marginal variances or a covariance matrix of the forecast. A full distribution forecast using TensorFlow distributions as a return type can be obtained from predict_proba. And up until the specific arguments, so for forecast intervals, you have coverage. For quantiles, you need to give it the quantile points you want to predict at. Up until then, the syntax is exactly the same as for the point forecast, and there are sensible defaults for the probabilities for the specific arguments. So coverage, for instance, will default to 90%, then the quantiles will default to 0.05 and 0.95 quantile points, which will give you except for interpretation, exactly the same as the default for the forecast intervals. Which forecasters support probabilistic forecasting can be retrieved by using the all estimators registry function. You need to filter tag capability predictive interval. If that tag is true, then the forecaster in question implements either by default or by native implementation, all 4 probabilistic prediction methods. So this method may take a while to run because it may have to crawl through the entire package. Some of these are compositors. In the case of a compositor, such as a pipeline, it means that depending on components, it may or may not support it, but logic is implemented if all is good for the components. So for instance, the PMD ARIMA models or Facebook Prophet support probabilistic forecasts out of the box. Okay, that was the quick start. Now, disambiguation, what is probabilistic forecasting? Intuitively, we want to produce a range of scenarios or an uncertainty around the forecast. So what does it mean? What is the range of variation or the nature of variation in the value that we expect to observe in the future? And it's a query to an algorithm. You ask the algorithm, what do you think are going to be high and low scenarios, and the algorithm doesn't need to be right, obviously, always. The algorithm can be wrong. It's what the algorithm tells you. And different algorithms, obviously, also will produce different probabilistic forecasts. From an interface view, we do the same as in point forecasting. So we specify the series we want to forecast, the values of it. specify exogenous data, which may or may not be observed or known up into the future. We specify a forecasting horizon, which encodes the indices at which we want to obtain forecasts at. And that is exactly the same as in point forecasting, which is covered, as I've said, in the basic tutorial. A recording of that is available from PyData Global 2021. Now, the key difference here is the output of predict, right? We have these 4 different predict functions, and depending on what you're asking from, the output will be in meaning or in format or in both. Well, always in meaning, but in format sometimes, different from what you get from the point forecast function predict. So it's going to be some object that encodes the probabilistic forecast, which could be, as we have just seen, a sequence of interval forecasts of lower and upper values for the quantiles, or it could be a full distribution. Right, and there's also a formal view on this, which I just skim over. Right, you have 4 different kinds of probabilistic forecasts that we're currently supporting and conceptually looking after, and that corresponds in a formal view to the variance forecast is a conditional variance, conditional on the data observed, as predicted by the model. Quantile forecasts are the quantiles of the predictive distribution. Interval forecasts are obtained from quantiles in a symmetric way. So for a given coverage, you want a symmetric interval where lower and upper excess are of equal probability, nominal probability. A distributional forecast returns in a symbolic manner. You're asking for a symbolic representation of the law or the distribution of the conditional, where the y prime here is the future data that you're trying to predict, y is the data you have observed, and all this has a true distribution, and we're asking for a prediction or an estimate of it. We're asking the algorithm for a prediction or an estimate of it. Quickly to note, different forecasts have different capabilities. Given that we have a variation over the return objects here, but we also have different metrics. So now we need to compare, for instance, a conditional variance prediction with an actual that is not a variance. The actual will be an observation. It will be a sample from the true y prime. And we will see also there's compositors that can just add functionality to add a type of forecast like the bootstrap. Okay, I'll skip this. There's a bit of intuition on the formal side here. You can read through it. And there's also references mentioned at the bottom. Frequent points of confusion, perhaps to mention. There's different concepts here which are relevant in using these definitions. Lower upper interval forecasts are equivalent to quantile forecasts at quantile points 0.5 minus coverage or plus coverage half. Except, of course, for the interpretation. For a symmetric interval, if you have a full symbolic representation of your distribution, then of course you can ask it for quantiles, or you can ask it for mean and variance. A full distribution encodes both the point forecast and the quantile forecasts. In general, so except for that, there's no exact relation between the different types of forecasts. So for instance, a point forecast, which is a mean forecast, in general, does not need to be equal to the median forecast, which would correspond to a quantile point of 0.5. And in general, the mean of a distribution can be smaller or larger than any quantile, as long as it's not 0 or 1. So there's, just to keep that in mind. If you look at the different packages in the ecosystem, and we've had a number of bugs ourselves as well, because we as developers ourselves found that confusing. It's really important to get this right. So common confusion is coverage versus the quantile of the lower. The coverage versus significance, so that's a 1 minus, right? So we had, for instance, a bug where When you made the coverage bigger, then the intervals became narrower, but that's just because the interfacing was done wrong. And getting all these things into a consistent interface format is also a bit of a challenge. There's also Bayesian posteriors or confidence intervals on the predictive mean, which should not, they're also intervals, but they shouldn't be confused with predictive intervals. Again, they all have formal meanings. I would recommend to read up on it if you're interested in probabilistic forecasting. The devil is really in the details. Okay, so back to doing that in SK-time, having a look at the various interfaces. So I'll look at one general thing. The prediction methods, they don't change state. So if you want to ask for multiple forecasts or a point forecast and a probabilistic forecasts, just call, for instance, predict and predict underscore interval. So up until the probabilistic prediction, the fitting works exactly the same. Of course, you need to use a forecaster that supports probabilistic forecasts. So you have data loading, define the forecasting horizon, construct the forecaster, and fit it. Now, then you have to run the probabilistic prediction method and specify the extra arguments, say if you want a coverage in predictive intervals that is different from the default value here. So let's say we want coverage forecast, interval forecast, it will look like this. Just call predict interval. And so that's the return that you get a column lower upper, and you can give it a vector of coverages, and then you will get here the second level here in the return. We'll have different coverages, and each of them will have a lower upper. If you have multiple variables, you get multiple values in the first column corresponding to variable names. You can, of course, also plot it, and then you get a nice interval forecast. So multiple coverages, as I've said, you can vectorize over coverages, so the same for the quantiles in the quantile forecast, and of course then the return object will expand. It's always a pandas data frame, except for the distributional forecasts, where the multi-index of the column ranges over potentially variables and coverages or alphas. Predict quantiles, really much the same, but now it's quantiles and not coverages, and because it's quantiles, they don't have a lower and upper. Same thing. So this is this plot shows 5 quantiles being forecast, 10%, 25%, median, 70%, so it's the quartiles except the min and max. That's usually going to be at infinity, and 10%, 90% plotted here. Predictive variances, there's just one predictive variance, so the marginal one just looks like the point prediction, but these numbers, of course, are variances, and as you see here, very sensibly, the variance increases as the predictive variance increases as you go forward in time, because the further it is in the future, the less certain the algorithm is about it, if it's a sensible algorithm. If you want a covariance, you get a covariance between forecasting horizon indices at the column and at the row. Predict proba gives you the full symbolic representation of a distribution. You need to have TensorFlow installed for that, and the return type is a TensorFlow distribution. If you are familiar with TensorFlow, if you want to ask for a marginal probability prediction, you have a batch shape that corresponds to the forecasting horizon length, and it's in the same sequence in the batch index. The event shape corresponds to the variables, so you can also model, of course, association, correlation between the different variables, but you don't get modeled association between the different time points. Of course, that's useful, for instance, if you want to compute something like a logarithmic loss where you need the marginal distribution. If you set marginal equal false, you get the full joint distribution, predictive distribution over all time points and variables. That's not implemented for many of, that's not necessarily implemented currently because not many methods support that. That's interface-wise, as I've said. The philosophy is designing an interface that you could implement against. So you get back here a y-pred dist. It's now a TensorFlow distribution. For the specific model, the theta, it's a normal distribution. So you can ask it for quantiles, and that should be consistent with the quantile prediction, and you can ask it for parameters, so you get location and scale, which in this case will be mean, and standard deviation of the marginal distributions in the prediction. Caveat: the different methods do not always need to be consistent with each other. Some algorithms also have a randomness in them, and that means even if you repeat them, you might get different results, and quantiles may cross over as well if the method itself doesn't prevent that. You can use probabilistic forecasts in the update predict in the streaming workflow, where you start with data, then let's say time progresses, you update the model with more data, and to predict in the following way. So let's say we start at end of 1950 and we want 12 months of predictions ahead, and every month we want to update the 12 months of predictions. So our 3 data batches with which we update look like this. Okay. So first, if we want to do this, then first we need to fit to the first batch, and the first prediction is obtained by a predict interval, and at each subsequent step we make an update and call predict interval again. And we do this as many times as we want. So it works well with the update predict workflow. Just to explain what we've done, right? We've expanded our data window. This is the blue thing here. We added one more row and made a prediction across the 12-month forecasting horizon, which is orange. So orange is the places, the indices where we make predictions for. So multivariate and hierarchical, I skim this over this. Different variables and hierarchical indices, we'll see this in a moment. They have row and column indices. And it works for all the forecast types. Metrics. So the metrics, again, I skip over this. SKTime currently implements a few metrics for interval and quantile forecasting. The pinball loss, for instance. And those metrics work exactly like point prediction metrics. The general form of how you evaluate the metrics keeps the general form of metrics. So first argument is the ground truth observation. The second argument are the predictions, but those predictions can take different forms. So for quantile forecast, it will be the data frame that contains the quantiles. For distributional forecast, it will be the TensorFlow distribution. It contains the symbolic representation of the distribution. And just like the point prediction metrics, we have classes, and those classes can be called using a function interface. So for instance, if we instantiate the pinball loss class, can then instantiate it as with the functional interface, y true, y pred. The predictive quantiles are what comes out of predict quantiles of the estimator, and then depending on how we average, right, all losses have different, you can set the weight to average, and you get the loss by quantile point, or the average over all quantile points, or by sample. So you can also get just a table of all the losses. I'll skim over that. And that way, it's fully compatible with the tuning interface and the evaluation interface. So you can stick now these probabilistic losses in the evaluation interface, just like you could any other loss. You need to provide it in the scoring argument. The evaluation interface will automatically recognize what type of a loss it is. So if you stick in a interval loss, it will call the predict interval interface of the estimator. You can use it in pipelines for tuning. And I want to mention, because I'm running slightly out of time, some advanced composition patterns here. There are estimators, compositors, which you can use to add probabilistic prediction capability to any estimator. So for instance, a naive variance estimate over the residuals. So you just take this compositor naive variance, you stick your favorite forecaster in. This one doesn't have probabilistic prediction, but after you stick it in this wrapper, it does have the capability, so there's some logic implemented. It works exactly like the reduction picture, the wrapper and the small thing inside. Then you can call it with the familiar interface. And of course, this is not the only way you could add, right? You could use the bootstrap that's not implemented yet, but contributions are very much appreciated. So there's a lot of interesting research around, for instance, how you turn your deterministic, your point forecasters into probabilistic ones. You can use it in tuning and AutoML, so just exactly the same compositors. You just pass a probabilistic score and it does the tuning across the probabilistic score, a forecasting grid search here, right? And the predictions just work like with the same interface. AutoML for multiplex using multiplex forecaster works exactly the same as in the deterministic case. Pipelines work exactly the same, and I also skim over that. You can have a look at it in the notebook. Here's some points. If you want to build your own probabilistic forecaster, you can look here at the details. We have in implementing your own estimator developer guide, there's a few extra points to look out for. They're all also mentioned in the extension template. I'm just highlighting them there for your own use. The check estimator utility can run as in the ordinary case to check which tests are running. So we have unified interfaces as a summary for probabilistic forecasting. We have probabilistic metrics, interfaces for evaluation. They work out of the box for all the composition patterns that you are familiar with in SKTime. For point forecasting, including the composite model building interface, it's also easily extensible. You just need to implement one of the probabilistic functions. There's some resources here. And questions?
So thanks a lot for your presentation on probabilistic forecasting. We just had one question on Slido about where to find the notebooks, and maybe we have time to
Yes.
answer one question here.
So where to find the notebooks has been posted in the Discord channel for this room. You just go to the Discord channel for this room. It's also at the start here. This is the link on the SKTime.org. All links have also been posted in the PyData Berlin Discord channel for this room, which is A5, A6.
Time for another quick question? In the audience, of course. I'm running, I'm going.
Thanks. Just a quick question on the training data and what experience you have, or how does it deal with data gaps? What I see a lot is that the training data is incomplete, so the times in between might be different. So you're lacking a sample for.
So if you have missing data or irregular sampling, you can just stick your estimator in a pipeline that deals with those aspects, or you can try an estimator that natively deals with irregularly spaced data. So for instance, we have the imputer. So the imputer, if you pipeline it with a forecaster, it first imputes the missing data and then runs a forecaster which might not deal with missing data, or you search for forecasters that have the missing data tag. And those are forecasters that out of the box can deal with missing data.
Thanks a lot for this presentation. We'll welcome next speaker, Daniel Bratling. And just while the speaker is setting up, just a reminder that we collect the question on Slido.com, and to join the conference, the hashtag is Pyber, Pyber. Thank you.
Okay. So thanks a lot. My name is Daniel Bartling. I work at as a data scientist at Mercedes-Benz AG. Mercedes-Benz is also a GitHub sponsor for SKTime. I think one of many, which is like testament to the great. I can take that off now, right? To the great potential, I think many in the industry see in SKTime. I'm going to speak about hierarchical, global, and panel forecasting. We will first talk about the general problem of hierarchical time series and why it's useful to have specific tools to model those. We will talk about hierarchical and panel data formats in SKTime, how SKTime represents these formats. And we'll also talk about the vectorization of forecasters and transformers, hierarchical reconciliation, which is very important in this context, global forecasting. We'll take a look at also one of the challenges of these models that we try to address here. And finally, we talk about the extender guide, similar to the way Franz just presented. So maybe first of all, just some background. What is a hierarchical time series? Why does it matter? So in business cases or in general or other domains, we often have the challenge that we have different structures of hierarchies. We have maybe here, for example, as you can see, for product sales, we have some products that are in certain categories. These categories add up to groups of categories, and we have a total. And depending on the problem, we're sometimes very much interested in the lower level, sometimes very much in the upper level, but sometimes also in all levels. And this is not trivial that we have estimators that perform well at all levels of the hierarchy and at the same time add up. Because, of course, often when we want to present finally a result, and then the first question, of course, is why doesn't it add up if you produce very good, accurate results at each level, but in the end the picture is not correct and clear, then you are have a problem often to explain your solution. So. Okay, so then we talk about a representation of hierarchical and panel data types. So in SKTime, we talk about 3 different categories we have here. We have series, panel, and hierarchical formats. Series is when you really consider every time series individually. Panel formats is when you have typically an identifier. You're mainly interested in an identifier. You have multiple time series that you are considering, but you are interested in an identifier that tells you to which time series now your observation belongs to. You track a panel of consumers across a certain length of time, for example. And hierarchical, finally, is the example that I just showed, where you can have a large number of different hierarchies at the same time. So for simplicity, we have different formats of how to represent data in SKTime, but we will now focus on the pandas data frame format in that case. And we call that information here we take some examples that we are interested in to see how these data types are represented. So first of all, we have the pandas data frame representation. I think the only important missing thing for the series type is that we have always an index. This must be monotonous. It can be an integer. It can be a range. It can be also a datetime index or a period index, and we can have an arbitrary number of columns that represent the time series that we are interested in. So for example, in this case, we have only one time series and an integer index. We can also have a bivariate case where you have 2 time series at the same time, also an integer index. So that's the base type we're interested in. And next we take a look at the panel type. As I mentioned here, we are mainly interested in tracking the different instances to which an observation belongs to. Instance in this case means the unique identifier of the time series. So for example, which person are we now tracking in the panel? And here we have a 2-column multi-index, and the second index always corresponds to the time period, to the time point, the first index is always our identifier. So the second index has the same, the time points index has the same restriction. It must always be the second index, else the algorithms get confused. So here you can have an example of how that looks like. We have two variables. We have the time points, again integer, and we have, in this case, 3 instances corresponding to 3 different time series that we are looking at. And finally, we have the hierarchical site type, called here PD multi-index higher, and basically just in the extension of the panel type, we have always the last index must be the time points index, and the indices before can refer to the hierarchy. So here, for example, we would then have maybe the products here in bar, and the product groups in foo to track where everything belongs to. So you can access these kind of indices. So what do we want to do with that? Now one approach that we could do is we simply want to fit a forecaster to every time series that we have here individually. So we are not interested in modeling any hierarchies, having any groups. We simply want that our models are applied independently to every instance we have here. And this can be done for this example data set that we have loaded here that conforms to the structure I already explained. When we simply call a forecaster just in a general way, we would do that on this data set, then it recognizes, our SKTime recognizes that there is a certain structure, a certain hierarchy in this data set, and it will maintain that structure and fit now individual models to every instance we just described. So all of these are individual, independent REMA fits, so there's currently, so the added benefit is here now, okay, we just provide the data frame, it will automatically detect that hierarchy and then provide the forecast. So we had a forecast horizon of 2, so you can see here we will always have the first 2 observations corresponding to that. You can access all these individual forecasters. You can easily see then every fit is independent, so every fit has also its own parameterization, so you can take a look at that. And see how that differs across the time series. And you can even, what Franz just showed, you can even take a look at prediction intervals in the same way, and then you will get the prediction intervals for the forecast derived in each group independently. We have an internal representation for that. If you want to take a look at the forecast, and then you can take a look at this inner M type, and it will tell you what kind of forecaster it is. Is it a forecaster that just can be applied to a series? Well, what we mean by that is it is a forecaster that doesn't understand or doesn't explicitly model any hierarchical information. So SKTime will then automatically apply, when it encounters such a hierarchical format, it will automatically vectorize and automatically apply independent fits. We could talk about different models in the future. For example, we are going to implement mixed effect models that can understand hierarchies, and then you will encounter here different data types, and then also the fits won't be independently vectorized, but will recognize that there is some added value to be drawn out of the hierarchy. There's a vast array of different kind of internal representations that are relevant here. We are not going through all of them, but you would encounter then, as we saw now for ARIMA, just PD series, and you would encounter different types, for example, multi-indexed here for a forecaster that can explicitly draw upon that information. So what are we going to implement here? We talked about providing forecasters that really explicitly model hierarchies. Also telling maybe the forecaster to be able to use the hierarchy level simply as covariates. I mean, that's something you can, of course, do in ARIMA, that you give the information about the hierarchy as a covariate. Exactly, that's something. Or also multivariate models like vector autoregression can then be fit to all time series at once. Now, what we next talk about is hierarchical reconciliation. So I already mentioned, typically in a problem, it's not a good situation if the hierarchies don't add up, of course. That's very difficult to explain, even if every high forecast here that you produced maybe has a good quality on its own. If they don't add up, then that's often a very undesirable feature. So what you can do, of course, always is what we call bottom-up reconciliation. You only model the lowest level of the hierarchy. So for example, you only model products. And then you would simply add up all the products to the total, and that then, of course, is consistent. But you often have the issue that maybe at the product levels, there's a very high volatilities. Products are phased out, phased in, some maybe out of stock or something like that. So you have a very high volatility when you just model at the product level, and this volatility adds up, resulting in a forecast at the top level of the hierarchy, your total, which maybe is really stable and has a nice seasonality and pattern, but suddenly it's a very wild forecast that it varies in a very significant way. So that's, and depending on the problem, can be a good solution, but often is not very desirable. There's another method just from the other way. You only model the top level of the hierarchy, and then you just take a look at certain proportions, maybe of the lowest level, how high is the proportional share of the lowest level, and you just break down the top level. But that, of course, ignores any peculiarities you have. Maybe some products at the lowest level are very seasonal, some not. So you are not able to model that. So that's also not really desirable. And therefore, what we are supporting here and what in general I think is like a bit of a standard is an optimal forecast reconciliation. You produce forecasts at all levels of the hierarchy, and then you adjust all of them to some degree. And there are different algorithms and different weightings that you can apply here. Then ultimately you have a forecast that typically produces good forecast at all levels, but adds up. And I think that's a very desirable property here. SKTime provides two functionalities that are important in this regard. The first is the aggregator, so simply adding up or aggregating up individual time series starting from the lowest level to the top level. And the other one is the reconciler that we just mentioned. So whenever you adjust forecasts at certain levels of the hierarchy, then you would use a reconciler. And we will now take a look at how that looks like in practice. So we always have what we always need in this regard is a total level. So what we showed you before is this foo bar structure where you have bar is the identifier of the individual instances, and foo would be like the categories. And what you can introduce here, and what we have in this example, is a total row. So the total row always refers in the first line here now to the total at the top level of the hierarchy, or to subload totals that you can see here in a total, and that would be the subtotals that you implement. So that would be a representation. But of course, we often don't start at that. So data set typically doesn't start at this SKTime compliant aggregation. And that's why we have an aggregation transformer. So we already saw the aforementioned problem. We passed the hierarchical information into the multi-index. And now we don't have, of course, this total structure. And that's why we take the aggregator. And that is what the aggregator does for us. So when we fit and transform the aggregator to the data set, then we will get all these totals. And we will have this compliant SKTime representation of how we would then represent the generation of all the levels of the hierarchy. And what we can now do is, for example, we take any forecaster that we have, and that's, I think, a relevant feature. I think there are other libraries where it's kind of linked, that you have at the same time to specify the forecaster and the aggregator, but here you can take any forecaster you want and combine it with an aggregator functionality. And then this example here, we would first apply the aggregator. We would first generate this aggregation structure, and then we apply a forecaster. And that would be the first case that I discussed. that you do a forecast at every level of the hierarchy at the same time. But this has the aforementioned problem that it doesn't add up. An alternative way, and this is corresponding to this bottom-up approach that we now mentioned, is to first fit to the non-aggregated data set forecaster and then add the aggregator after that. And then you will get fully consistent forecasts that correspond to the bottom-up approach. So there's no reconciliation at this point because we don't adjust anything. And the advanced reconciliation, on the other hand, that would be using the functionality of the reconciler. So we can first fit, for example, the aggregator, then the forecaster, and then a reconciler. And this is now an ordinary least squares reconciler. I think we have currently implemented also a weighted least squares reconciler, and then we would have this mentioned behavior that all forecasts at all levels of the hierarchy are adjusted. So we have at the same time relatively good forecasts at all levels of the hierarchy and this coherence that we want. So what is the roadmap, or where we do we want to go? There's a technical issue here. We currently, in the book of Hindman, which is like the standard, there are several reconciliation methods with the current structure of the pipeline. We are not able to implement all of them, so that's something we just want to extend in this way. We also want to implement more reconcilers as a result of that, that we have more different methods. And we also want probabilistic reconciliation, which means like what Franz just showed, that we have these confidence intervals or quantiles. And of course, you can do also hierarchical reconciliation across different forecasts and different quantile forecasts. So that's also something that we are working on. Now I will show the next use case, which is global forecasting. Global forecasting, what do we mean by global forecasting? Global forecasting distinguishes itself from univariate forecasting because you do not fit individual time series always in an independent way, but instead you pass a lot of time series to a single forecaster. Why is that desirable? First of all, in the time series domain, we often have the issue that we don't have so much observations going back in time. So that's typically just a problem. Maybe we just started collecting the data, and therefore sometimes it's very difficult to implement complex models. We know, for example, we want to forecast production volumes in a plant, and we have information, complex information about the production program. We have information about the capacity. But if we now do individual forecasts for every time series, then it's very, very difficult for the time series to understand the relationship between the volumes that are finally resulting and all this information you want to feed inside. Maybe you know really a lot about how your process works, but simply because you don't have so much observation going back into time, often it's an issue to help the forecaster understand that information. And that's where global forecasting comes into play. So here the idea is that we fit, if we are able to observe, I don't know, hundreds or thousands or 10,000 or several thousand of the similar processes, similar productions of items, similar evolutions of balance sheet accounts, different accounts, and you think there's some similarity between the data generating process behind generating that, then you can feed everything into a global forecasting model, and suddenly you have a much larger database, and you can also model much more complex relationships. This doesn't work, of course, if the main driver is the evolution of time, and because that's something you can't extend. But if it's simply because you didn't observe your process enough times, because there are some relationships independent of, I don't know, the purely time-driven way, then this works very well. And that's why also we have a very good performance of these models in many competitions that are relevant here. So we take a look at one example that's based on the popular M5 competition. Here we can say, okay, we model every product by certain instances. This is how, for example, the Y now looks like at the top level. So we have this inter-instance structure, we have the time-stamp structures, and that conforms to products. And we have lots of exogenous information, also in the same way with instances identifying whether this information belongs to. And we model this with the panel data type that we already mentioned. And we can use all this kind of exogenous information. So what we first do is, again, apply this temporal train test split, and this will now understand that there's a structure, that there are different instances, so it will split every instance conforming to that structure. So in train, we have always, for all instances, the same time points, and in test, we always have the same time points. We will now explain how we implemented or what our forecast that we chose for this was a tree-based model. Typically, tree-based models have issues in univariate forecasting because you don't have so much data. They are very good at modeling complex dependencies, but in global forecasting, as we said, we have lots of data. For example, in M5, I think in total we had 43,000 time series. SKTime supports all kinds of tree-based models. We just have random forest regressor here. But what is the big caveat here? These models are not really designed for time series tasks. So they are assuming every observation is independent in principle, and that's why we need to provide information that captures the time series dynamics. And for that, we implemented a window summarizer that constructs features that help the algorithm understand the time series dynamics. So for example, with this notation that we specified in the dictionary, we are able to generate a lag, we are able to generate a rolling mean calculation across a window of length 3 or 6 in this case, and lagged by a period of 1 and 3. And we can also calculate standard deviations that way. So that would be the notation here we use for the window summarizer, always referring to the observation I want to forecast and generating then different functions. And by default, we have implemented all the pandas, or you can access all the pandas native rolling window functions, which are very fast when you apply them in this group by fashion, and also parallelized. But you can also provide your own functions. I think what was very useful is, for example, providing means of different window length and different lags to understand what is the level of the forecast you want, and also maybe if you track different windows, you can see the tendency. But also things like skewness or kurtosis were very helpful to also see the tendencies where your forecast should go. But you can also provide every function that you think is usable or makes sense. Typical examples in the M5 was counting how many zeros you had, for example, but you can define anything and provide it here, and then this will be also implemented and will track exactly how it's look like. So here, for example, everything that is above 700, I think the column name is wrong, but the function definition is correct. You can also apply this window summarizer not only, so this was about helping your model understand the evolution of your Y, so that you give it the sense of the time dynamics, but you can also apply the same, of course, to exogenous features. So maybe you think it's relevant what was lags about holidays, for example. A day before a holiday often is also relevant when you want to model sales, because everyone buys more. And the same for maybe sales prices or things like that. And then you can use the window summarizer in a forecasting pipeline, telling it which exogenous information you want to cover. You can also specify different dictionaries, different functions that you want to have applied, and then this information will be used. So that's the other implementation of that window summarizer. Now, if we want to implement that for our typical problem, then we use a make reduction function. What that normally does is it provides for every observation that you want to forecast, it provides all past observations just as raw values. You can specify a window length of 20, and then you will get the past 20 observations, but raw without any feature engineering. But if you want, but this is typically not very efficient because you cannot really model the time dependence just by passing raw values, at least not with tree-based models, and that's why you typically want to apply your Windows summarizer, which will then maybe instead of the 20 raw values, give you the mean of the past 20 observations and the standard deviation of the past 10. Whatever you specify here, and you can specify within the make reduction functions that Windows Summarizer that will do that work for you. Another feature that also is relevant and that is also not understood by tree-based models by default is calendar information. So if you just pass a date column, there's not much information that can extract from it. It will convert it to an integer and that's it. You typically want to provide information about it. Day of the week effects can be very relevant, maybe seasonalities, they're being different in spring and in summer. Month beginning can be different to month end due to salary effects. All these kind of things you want to model, and for that we have a daytime features transformer, and that will then take a look at the time points column and generate features that are relevant here. So you can just call it and pass the frequency, and then it will automatically generate some sensible features. In this case, for daily data, you get month and weekday, but that's an automated functionality. We support these kind of periods currently, and you can specify every period that you want or that you think is relevant. So for example, when you say I'm interested in the week of the month and the day of the quarter, then it will, and you can pass that to this transformer, then it will generate you that information. Often this example probably will not be very useful often, but depends on the question you are trying to tackle. So putting it all together, here we have this forecasting pipeline. You can say, okay, I have certain dynamics for my events, for the holidays. I'm interested in different legs. So here in this quarks argument, I can specify then what kind of features I'm interested in. Then maybe another column, I want to specify other information in. So you have for the snap day, you have days, you have certain other dynamics, and you can implement that as a next step in the forecasting pipeline. Then you add on top of that daytime features, in this case daily data, and then finally you have your forecaster. We talked about it, that within that forecaster, this make reduction function, where we then apply the Windows summarizers we want to apply to the Y to help the model understand the time series dynamics. And then finally you can fit that, and it will then return your forecasts that correspond to the structure of the time series that you provided. Exactly. So here you can see, in this case, 2 products. You will get individual forecasts for these 2 products. What is the road ahead? What we implemented and what we thought was relevant with regards to global forecasting is these daytime features with the summarizer, the hierarchical data type, these adjustments to reduce to allow an efficient and performance-intensive, useful implementation that is parallelized. Because often these problems can become so huge and that the performance is very important. One area of further research that we have would be cross-validation, because you saw we can specify this dictionary, but that's of course quite manual task. So typically there's some expertise you have. You can of course for cross-validation provide all kinds of dictionaries, but typically you want to have that generated. And here we are talking about different approaches. One would be, for example, to auto-detect based on autocorrelation and seasonality what kind of features you really then generate ultimately. Or also you can take a look at the feature importances to identify relevant features. So that would be then more like an automated tuning strategy. Other things that we are talking about is extrapolation in time series. That's of course very important, but not really supported by tree-based models. Okay. Thanks. And there are some methods to help you to help these models extrapolate. You can talk about trend removal and addition. Here again, then the question is: do you want to remove trends in each individual time series? Do you want to identify common trends and remove them commonly and add them up after that? But you can also do some post-processing. So here we are still discussing where we want to go as a next step. And of course, quantile regression. For example, at the M5, this was a split competition. We had point forecast, but we also had quantile forecast. These tree-based models performed best for both of these challenges. And that's what Franz already showed us. And here, that is, however, currently also not supported. So that's some things where we, of course, are also very interested in any additional contributors that would try to or would support us in that regard. Finally, we talk about the extension guide. You can build your own hierarchical forecaster. Here is some guidance on how to do that. We always have this check estimator function that will run you through all the tests that are relevant in this regard. So if you want to implement anything on your own, that's very helpful. And of course, for hierarchical type, you would then specify the correct inner M type. We talked about it, especially multi-index hierarchical. And that's I think, a guide on how to proceed here, if anyone is interested. And here we also come now to the next point. Franz?
Well, together. So, thanks a lot, everyone. And I think we're approaching the end of our presentation. Just to reiterate this, as we've said at the start, SK-Time is very much a community-based project. We're looking very much after our contributors and try to involve them in community operations as well as events. This summer we'll have the Google Summer of Code. Applications are still possible until April 19. You can sign up for mentoring and community collaboration sessions on Fridays. You can join them on Discord. Just drop in and say hello. We'll have an onboarding event May 25 to 27 and the yearly developer sprint on June 27 to July 1. Any questions?
Thanks a lot for the presentation. And yes, we have a few questions on Slido. Yeah, we have a bit of time for questions. I will go first on the...
So can I maybe quickly say a thing? Yeah. So I've seen people try to run the notebook that currently will break on Binder because that relies on Conda, and the newest version is not yet out on Conda. So you need to use either the developer version or a pip install that should work. Once the release is on Conda, the Binder should also run.
It fails with the pip install. It fails with the pip install.
Well, we have, so please raise that then in the community channels on Slack and or on raise a bug report on SK-Time.
Yeah, I've seen some people here in the audience encountering that. One issue is often the profit library. You need to pay attention to what is a hard dependency and what is a soft dependency.
If your operating system is Windows, right? Pip install, if you install with all extras, does not work on Windows with all extras. So if you go to the installation instructions, there is a specific sequence of commands you need to run for Windows if you want all the soft dependencies.
Yeah, so that's not related to SK-Time, but some dependencies
it is,
have. Yeah, okay, but not something we can fix, let's say, like that.
But even Conda install is not working. I'm trying Conda install.
You need to install from Conda Forge?
We can look later into it.
Yeah, so I'm really sorry. It's hot off the presses, and maybe there is a bug.
Let's come to the questions.
Yeah.
Okay. Question. Yeah, we have a few questions on Slido. The first question, how many layers of hierarchy are supported in SK-Time?
No limit.
Arbitrary number of. So the hierarchical data type, at least by definition, supports 3 or more layers. Of course, not every algorithm will be able to deal with that.
Okay. A second question from Anonymous. Is it possible to access the parameters of the specific models? For example, would I be able to get profit trend, holiday coefficient through SK-Time?
Yes. So SK-Time supports the get and set params interface of scikit-learn and is fully compatible with that. If you use get params with the deep argument, you can see all the parameters. So you mean hyperparameters or the fitted parameters? You have to. So some estimators implement a get fitted params method. That is though not implemented with nesting. So you may have to look through the underscore attributes if you're looking for fitted parameters.
I have then a question about type error when the SK-Time version 0.11.1 is installed, and yeah, it raises a type error at fit with an unexpected keyword argument fh, but maybe it's something that can be raised somewhere else. Okay,
Open the bug report.
Yeah. Is visualization of hierarchical time series supported in SK-Time, or is it even possible?
It's not supported. Would be a nice thing to have. So open an issue with a feature request or contribute it yourself by a pull request.
Okay. Defining meaningful thresholds for the window summarizer is an art. Any support from SK-Time to evaluate the most suitable time window?
Yeah, that's what we discussed and where we want to go. We have different approaches we discussed here. One would be like a hand tailored. You provide a complexity argument, you provide your frequency that you have, and then some common useful things would be implemented. But ideally, of course, you want to have some detection about that. We have some ideas on how to proceed here, but there's nothing currently implemented. That's what I mentioned. It's really a kind of a art currently, so we don't have an out-of-the-box solution here.
The interesting roadmap item, extending grid search and evaluation for hierarchical data types. So having the window splitter, grid search, and evaluation integrated, then you could tune, for instance.
Okay. Next question. Do you have any support for scaling, like multiprocessing usage in Cloud, Spark, etc.? For Prophet, there are some resources for setting it up with PySpark?
Not directly, no. Of course, you can always embed your code, and there is parallelization which some estimators implement, but there is not this overarching framework just to run it on PySpark. It sounds like a big effort. I mean, we're getting a lot of requests for that, but of course, we're a volunteer-driven project mostly, so that might be something for the next big roadmap period.
Okay. Assuming you have daily data and retain once a week, such that during cross-validation you can predict a full week at once, how do you deal with gaps from forecast horizon?
Gaps in the forecast horizon?
Yeah. FC.
It can have gaps. Sure. Yeah. So an estimator, the interface requires that you can implement. So that the forecast horizon can have gaps. Of course, a number of estimators can't deal with that, so what in this case we do, we just fill in the gaps and then remove them again. But that is really the estimator's business.
Yeah.
Then last question I have on Slido. Thanks for the great presentation. I would like to know if I can use SK-Time to denoise time series.
Denoising. So that's an interesting topic. We have an open issue on denoising and things like the Kalman filter. You could use currently a PCA or Hampel filter. Yeah, we have about bug reports around it, so you may want to try. And Kalman is a contribution as an interface to happen, hopefully. It's not that well supported at the moment, right? So it might be a nice thing, again, to contribute.
We still have 5 minutes to take 1 or 2 questions in the audience.
You could use exponential smoothing in sample. You could use exponential smoothing in sample. That would also work.
Okay, I see some questions.
Hi. Do you already have an interface to Gluon TS, for instance, for hierarchical forecasting?
No, it's an open issue.
Okay.
So it's one of the big things on the please interface list. Pull requests.
So I see that you had some models with hidden variables. For instance, you talk about Kalman filters. But is it possible to share hidden variables between different panel data or different time series?
Okay, I mean that's a model concern. So there is no abstract interface element which allows you to share fitted parameters between the models. Of course, you can implement it for your model, but then you would need to wrap it in the general interface. There is also a parameter extractor, is a transformer, which you could which you can use in feature extraction, and it takes out of the forecaster, I think, the parameters, but that might not be exactly what you want. Is it?
Okay.
So you want models to share parameters between. Yeah, it's an interesting question whether how that would look on a framework level, sharing parameters between models, because then you would also need to have a model that inputs. So where do you input the parameters, and then how does the other model know what parameters it's getting?
Okay. Maybe one more question.
Interesting.
Yeah, one more data science question. Like you have these daytime features, like week of the year or something, and then you have the problem that 1 is very close to 52 or something. Like, what is your? Do you have a suggestion how to deal with it? I know there's like sinus and cosinus encoding for it.
Yeah.
But like just because you deal with these things probably, so maybe you have an idea what's a good solution.
So this Fourier terms approach is an alternative way where you have more smoothness between the different realizations, right? So I'm not sure about, I completely got your question, but for example, if a day of the week, Monday and Tuesday are more linked and not really independent, then you can use Fourier terms, and that's a thing that we talk about. Or that we want to implement, but it's currently not supported. So currently you have these dummy features, and that's basically everything is independent. If you think there's some sort of smoothness, then that's... Was that a question? Or?
Yeah, I'm
I
not
thought
sure.
we did have Fourier
sure,
features
like
somewhere. Didn't we have Fourier
Yeah, I
features
think we
somewhere?
have a Fourier transformation, but the Fourier terms to be used in that way, I'm not sure about.
Yeah, but you would just put it, wouldn't you just put it in the make reduction and then you use it as a transformer? Then those Fourier terms are added as a column to the exogenous thing.
I have a development version for this daytime features similar for this Fourier terms, but I have not implemented yet.
Yeah, but Fourier features are, I think, already in.
Yeah, okay, I'm not sure about that. Yeah.
And then you could, you could plug it in. No,
Okay, yeah,
so
then
I
you could
suspect.
plug it in. Yeah,
I mean,
I don't know all the functions.
It might, of course, break, but in theory, you would plug it.
I still have it on
You
the
would take
agenda.
the Fourier feature transformer and plug it into the transformer's argument of the make reduction.
Thanks a lot again to the speaker and the presentation today.